matter, but let's do A. Consider psi is equal to A on phi E. Okay? What can you say about this state? Well, it's the state you get by taking this wave function and acting with A. Not terribly illuminating. However, E on psi is equal to what? Maybe this has some nice property under acting with E. This is equal to E on A with phi E. Now this is tantalizing, because at this point, it's very, look, that E, it really wants to hit this phi, right? It just really wants to. There's E, it would be great. The problem is not there. There's an A in the way. And so at this point, we add 0. Okay, this is a very powerful technique. This is equal to E A minus A E plus AE. By E. Okay? But that has a nice expression. This is equal to EA minus AE. That's the commutator of E with A. Plus A. Well, what's E acting on phi E? Well, actually, let me just leave this as AE. So what have we done here before we actually act phi E? What we've done is something called commuting an operator through. So what do I mean by commuting an operator through? If we have an operator A and an operator B and a state F, and I want A to act on F, I can always write this as, this is equal to the commutator of A with B plus BA acting on F. So this lets me act A on F directly without B, but I have to know what the commutator of these two operators is. So if I know what the commutator is, I can do this. I can simplify it. This is called, when one does this, when one takes AB and replaces it by the commutator of A with B plus BA, changing the order, the phrase that one uses is, I have commuted A through B. Okay? And commuting operators through each other is an extraordinarily useful tool, a useful technique. Now let's see why. So here, what's the commutator of E with A? Oh, we just did that. It's minus H bar omega A. And what's AE on phi E? What's E on phi E? E. Right, exactly. Plus E A on phi. And now we're cooking with gas. Because this is equal to H minus H bar omega A plus EA. I'm going to plot this common factor of E of A. Okay? So if I plot the common factor of A plus E A phi E. And now I'm going to just slightly write this instead of E or minus H bar omega plus E, I'm going to write this as E minus H bar omega. I'm just literally changing the order of the algebra. E minus H bar omega. And what is A E? Psi. That was the original state we started with. Psi. Well, that's cool. If I have a state with energy E, and I act on it with the operator A, I get a new state psi, which is also an eigenstate of the energy operator, but with a slightly different energy eigenvalue. The eigenvalue is now decreased by H bar omega. Cool? And that is what we wanted. Let's explore the consequences of this. So, if we have a state with eigenvalue E, we have phi E, such that E on phi E is phi E. Then the state A, phi E, has eigenvalue as energy. Eigenvalue E minus H bar omega. So I could call psi, I could just call this phi sub E minus H bar omega. It's an eigenfunction of the energy operator, the eigenvalue E minus H bar omega. Agreed? Do I know that this is in fact properly normalized? No, because 12 times it would also be a perfectly good eigenfunction of the energy operator. So this is proportional to the properly normalized guy with some at the moment unknown constant coefficient normalization. Are we cool with that? So now let's think about what this tells us. This tells us if we have a state phi E, which I will denote its energy by this level, then if I act on it with A phi E, I get another state where the energy instead of being E is equal to E minus H bar omega. So this distance in energy is h bar omega. Cool? Let me do it again. Let's act A on phi e. By exactly the same argument, if I make psi is equal to A on A phi E, A squared phi E, I get another state, again separated by h bar omega. E minus 2h bar omega. Turtles all the way down. Everyone cool with that? Let's do a slightly different calculation. So, okay, but before we do that, so I want to give A a name. Okay. A does something really cool. When you take the state phi E that has definite energy E, it's an energy eigenfunction, and you act on it with A, what happens? It lowers the energy by h bar omega. So I'm going to call A the lowering operator, because what it does is it takes a state with phi E, with energy eigenvalue E, to a state with energy E minus h bar omega. And I can just keep doing this as many times as I like and build a tower. Yes? Very good question. Hold on to that for a second. We'll come back to that in just a second. Okay. So this seems to build for me a ladder downwards. Everyone cool with that? But we could have done the same thing with a dagger. And how does this story change? What happens if we take a dagger instead of A? Well, let's go through every step here. So this is going to be E on a dagger. And now we have E, a dagger, E, a dagger. What's E with a dagger? E dagger. E with a dagger is equal to? Take even with a plus. And again, psi, same thing, because the a dagger factors out. Yeah? So, we go down by acting with A. We go up by acting with a dagger. And again, the spacing is h bar omega. And we go up by acting with a dagger again. So A and a dagger are called the raising and lowering operators. A dagger, raising operator. A dagger, phi E plus h bar omega. Okay? So, what that lets us do is build a tower of states, an infinite tower of states. We're given a state, we can walk up this ladder with a raising operator, and we can walk down it by the lowering operator. So now I ask you the question, why is this ladder evenly spaced? There's one equation on the board that you can point to. Well, I guess two technically. There are two equations on the board that you could point to that suffice to immediately answer the question, why is the power of energy eigenstates evenly spaced? What is that equation? Yeah, those commutators. These commutators are all we needed. We didn't need to know anything. We didn't even need to know what the potential was. Right? If I just told you there's an energy operator E and there's an operator A that you can build out of the observables of the system, such that you have this commutation relation, what do you immediately know? You immediately know that you get a tower of operators because you can act with A and raise the energy by a finite amount, which is the coefficient of that A in the commutator. Yeah? This didn't have to be the quantum mechanics of the harmonic oscillator at this point. We just needed this commutator relation, E with a dagger. And one of the totally awesome things is how often this shows up. If you take a bunch of electrons and you put them in a magnetic field, okay? A bunch of electrons, very strong magnetic field, what you discover is the quantum mechanics of those guys has nothing to do with the harmonic oscillator on the face of the magnetic field, Lorentz force law, the whole thing. What you discover is there's an operator, just usually called A, but it depends on which book you use, N or M or L. There's an operator that commutes with the energy operator in precisely this fashion, which tells you that the energy eigenstates live in ladder. They're called Landau levels. This turns out to be very useful. Any of you who are doing UROC in the lab that has graphene or any material really, magnetic field, but this matters. So this commutator encodes an enormous amount of the structure of the energy eigenvalues. And the trick for us was showing that we could write the harmonic oscillator energy operator in terms of operators that commute in this fashion. Yeah? So we're going to run into this structure over and over again. This operator commutes with this one, the same operator times a constant. That tells you have a ladder. We're going to run into that over and over again. When we talk about Landau levels, we get there. When we talk about angular momentum, we get the same thing. When we talk about the harmonic oscillator, we'll get the same thing. All right, sorry, the hydrogen system, we'll get the same thing. Okay. So, second question. Does this ladder extend infinitely up? Yeah, why not? Can it extend infinitely down? Why? Well, okay, people are saying ground state. Well, we know that from the brute force calculation. But without the brute force calculation, can this ladder extend infinitely down? Brilliant. Okay, good. And as you'll prove on the problem set, you can't make the energy arbitrarily negative. But let me make that sharp. I don't want to appeal to something we haven't proven. Let me show you that concretely. The energy expectation value in some state, in any state, right? The energy expectation value can be written as the integral of phi complex conjugate, let's say in state phi complex conjugate e phi. But I can write this as the integral, let's say dx, integral dx. Let's just put in what the energy operator looks like. So psi tilde, we can take the Fourier transform, right? The psi tilde of p squared upon 2m, p for the kinetic energy term, plus the integral, and now I'm using the harmonic oscillator, plus the integral dx of psi of x, norm squared, m omega squared upon 2x squared. Okay. A little bit of a quick move there, doing the Fourier transform for the momentum term and not doing the Fourier transform, but it's okay. They're separate integrals. They can do this. And the crucial thing here is this is positive definite. This is positive definite. Positive definite. Positive definite. All these terms are strictly positive. This must be greater than or equal to 0. It can never be negative. Yeah? So what that tells us is there must be a minimum E. There must be a minimum energy. And I will call it minimum E naught. Okay? We can't lower the tower forever. So what is that? How is this possible? How is it possible that, look, on the one hand, if we have a state, we can always build a lower energy state by acting with lowering operator A. And yet this is telling me that I can't. There must be a last one where I can't lower it anymore. So what reaches out of the chalkboard and stops me from acting with A again? How can it possibly be true that A always lowers the eigenfunction, but there's a least one that can't be lowered any further? Non-normalizable is a good guess. Very good guess. Not the case. Because at this point, from this argument, we don't even use wave functions. That would be bad. Yes, exactly. So that would be bad, but that doesn't. I mean, that's just saying that there's an inconsistency here. So I'm going to come back to your answer, non-normalizable. It's correct, but in a sneaky way. Here's the way it's sneaky. Consider a state A on phi. Let's say this is the lowest state. Okay, the lowest possible state. It must be true that the resulting state is not phi minus h bar omega. There can't be any such state. And how can that be? That can be true if it's 0. So if the lowering operator acts on some state and gives me 0, well, okay, that's an eigenstate, but it's a stupid eigenstate. It's not normalizable. It can't be used to describe any real physical object. Because where is it? Well, it's nowhere. The probability density. You can find it anywhere. It's nowhere. Nothing. 0. So the way that this tower terminates is by having a last state, which we'll call phi 0, such that lowering it gives me 0. Not the state called 0, which I call this, but actually the function 0, which is not normalizable, which is not a good state. Okay, so there's a minimum E naught, and associated with that is a lowest energy eigenstate called the ground state. Now, can the energy get arbitrarily large? sure, that's a positive, definite thing, and this can get as large as you like. There's no problem with the energy eigenvalues getting arbitrarily large. You can just keep raising and raising and raising. I mentioned that because later on in the semester, we will find a system with exactly that commutation relation, precisely that commutation relation, where there will be a minimum and a maximum. Okay? So the commutation relation is a good start, but it doesn't tell you anything. We have to add in some physics, like the energy operator is bounded below for the harmonic oscillator. Questions? Yeah.
So you basically tell me this ladder has to exist if I'm a particular FBI I can construct a ladder. How do I know that I can't construct other intersecting ladders?
Yeah, that's an excellent question. So when I remember vividly when I saw this lecture in 143A, and that question plagued me. And foolishly, I didn't ask it. So here's the question. The question is, look, you found a bunch of states. How do you know that's all of them? Okay. How do you know that's all of them? So let's think through that. That's a very good question. I'm not going to worry about normalization. There's a discussion of normalization in the notes. How do we know that's all of them? So, yeah, that's a little bit tricky. So let's think through it. Imagine it's not all of them. In particular, what would that mean? In order for there to be more states than the ones that we've written down, there must be states that are not on that tower. And how can this thing's totally falling apart? How do we do that? How is that possible? So there are two ways to do it. So here's my tower of states. Okay. There's my tower of states, and I'll call this one phi 0. Okay. And so I raise with a dagger, and I lower with a. So how can it be that I missed some states? Well, there are two ways to do it. One is there can be extra states that are in between, right? So let's say that there's one extra state that's in between these two. Okay, just imagine that's true. If there is such a state, by that commutation relation, there must be another tower. Right? So there must be this state, and there must be this state, and there must be this state, and there must be this state. Yeah? Okay, so that's good so far, but what happens? Well, A on this guy gave me 0. Right? So A on phi naught was 0, and this is going to be some phi tilde naught. Suppose that this tower ends. Okay? And now you have to ask the question, can there be two different states with two different energies with A naught? Can there be two different states that are annihilated by A naught? Well, let's check. What must be true of any state annihilated by A naught? Well, let's write the energy operator acting on that state. What's the energy of that state? Energy on phi 0 is equal to h bar omega. This is a very good question, so let's go through it. So it's equal to h bar omega times a dagger A plus 1/2 on phi 0. Okay. But what can you say about this? Well, A annihilates phi 0. It gives us 0. So in addition to A being called the lowering operator, it's also called the annihilation operator. Because, I don't know, we're brutal and we're like species. So this is equal to h bar omega. This term kills phi 0, again, if it kills. And give me a 1/2 left over, 1/2 h bar omega phi 0. So the ground state, any state annihilated by A must have the same energy. Yeah? The only way you can be annihilated by A is if your energy is this. Cool? So what does that tell you about this second ladder of hidden states that we missed? It's got to be degenerate, right? It's got to have the same energy. Yeah? I drew that really badly, didn't I? Those are evenly spaced. So it's got to be degenerate. However, Martin proved for you the node theorem last time, right? He gave you my spread argument for the node theorem. And one of the consequences of that is that in the system with bouncing, in the system with conventional you can never have degeneracies in one dimension. We're not going to prove that carefully in here, but it's relatively easy to prove. In fact, if you come to my office hours, I'll prove it for you. It takes 3 minutes, but I don't want to set them out for you. So, how many people know what the Wronskian is? That's awesome. Okay, so I leave it to you as an exercise to use the Wronskian to show that there cannot be degeneracies in one dimension. Which is cool. Anyway, so the Wronskian for the differential equation, which is the energy eigenvalue equation. So, there can be no degeneracies in one-dimensional potentials with bound states. So what we've just shown is that the only way that there can be extra states that we missed is if there's a tower with exactly identical energies all the way up. But if they have exactly identical energies, then it's degenerate, but we can prove that there can't be degeneracies in 1D. So can there be an extra tower state we missed? No. Can we have missed any states? No. Those are all the states there are. We've done it without ever solving a differential equation just by using that commutation relation. Now at this point, it's very tempting to say like that was just sort of magical mystery stuff. But what we really did last time was very honest. We wrote down the differential equation, we found the solution, we got the wave functions. So, Professor Adams, you just monkeyed around at the chalkboard with commutators for a while, but what are the damn wave functions, right? So, we already have the answer. This is really quite nice. Last time we solved that differential equation, right? And we had to solve that differential equation many, many times, different levels, but now we have a very nice thing we can do. What's true of the ground state? Well, the ground state is annihilated by the lowering. So that means that A, acting on phi 0 of x, is equal to 0. But A has a nice expression, which, unfortunately, I erased. Sorry about that. So A has a nice expression. A is equal to x over x naught plus I p over p naught. Right? And so if you write that out and multiply by some appropriate constants, this differential equation, this becomes the following differential equation. Well, the x is just multiplied by x, and the p is take a derivative with respect to x multiplied by h bar upon I. And multiplying by I over h bar to get that equation, this gives us dx plus p over h bar x naught. Whoops. P naught. Sorry, that shouldn't be an I. That should be p naught. Good. X on phi 0 is equal to 0. And you solved this last time when you did the asymptotic analysis, right? This is actually a ridiculously easy equation. It's a first-order differential equation. There's one normalization, or there's one integration constant. That's going to be the overall normalization. So the form is completely fixed. First-order differential equation. So what's the solution of this guy? It's a Gaussian. And what's the width of that Gaussian? We'll look at p naught over h bar x naught. P naught over h bar, well, we know that p naught times x naught is twice h bar, right? So if I multiply by x naught on the top and bottom, get 2 h bar. The h bars cancel. So this gives me 2 upon x naught squared. You remember I said it would be useful to remember that p naught times x naught is 2 h bar? It's useful. So it gives us this. And so the result is that phi naught is equal to, up to an overall normalization coefficient, e to the minus x squared over x naught squared. Solid. Okay? So there, we've solved that differential equation. It's the second easiest differential equation. It's our first order differential equation with a linear term rather than a constant. We get a Gaussian. And now that we've got this guy, look, do you remember the third Hermite polynomial? Because, if you want, we know that the third excited state is given by h3 times this Gaussian, right? Do you remember it off the top of your head? Here's how you solve what it is. How do we get phi 3? First off, how do we get phi 1? How do we get the next state in the ladder? How do we get the wave function? Raising operator. But what is the raising operator? Oh, it's the differential operator I take with, okay, but if I had a dagger, it's just going to change the sign here. So now how do I get phi 1? Phi 1 is equal to, up to some normalization, okay, dx minus 2 over x naught squared, x naught, phi 0. Cool? So now, do I have to solve a differential equation to get the higher states? No, I take derivatives and multiply by constants. Okay, so to get the third Hermite polynomial, what do? You do this 3 times. This is actually an extremely efficient way. It's related to something called the generating function. Extremely efficient way to write down the Hermite polynomials. They're the things that you get by acting on this with this operator as many times as you want. That is a nice formal definition of the Hermite polynomials. The upshot of all of this is the following. The upshot of all this is that we've derived that without ever solving the differential equation, the spectrum, just from that commutation relation, I cannot emphasize this strongly enough, just from the commutation relation, EA is minus A times a constant, and EA dagger is A dagger times a constant, we derive that the energy eigenstates come in a tower. You can move along this tower by raising with the raising operator, lowering with the lowering operator. You can construct the ground state by building that simple wave function, which is annihilated by the lowering operator. You can build all the other states by raising them, which is just taking derivatives instead of solving differential equations, which is hard. And all of this came from this commutation relation. And since we are going to see this over and over again, and you will see this depending on how far you take physics, You will see this in 805. You will see this in 806. You will see this in quantum field theory. This shows up everywhere. It's absolutely at the core of how we organize the degrees of freedom. This structure is something you should see and declare victory upon seeing. You should see this and immediately say, I know the answer, and I can write it down. Okay? In the next lecture, we're going to do a review, which is going to introduce a slightly more formal presentation of all of these ideas. That's not going to be material covered on the exam, but it's going to help you with the exam, which will be on Thursday. See you Tuesday.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Hi, everyone. I'm in a very good mood today. Nothing to do with the class, but I'm having a baby.
Oh,
So,
congrats, Alan. Like 5 years ago. Shout out.
that's exciting. So if I just start giggling, you'll know why. 6 months, if I just weeping on the ground, you'll also know why. So today we're going to do 2 things. The first is I'm going to give you, the first is review a little bit of practice for the exam we're going to have on Thursday. So let me tell you a little bit more about the exam. The exam, by the way, has been rescheduled to be in 6120, not in Walker Gym. So it's going to be the usual place. We're not moving. And the reason is I'm changing the format on this exam, in part to make it a little less of a burden to everyone, but also in part because I've been struggling with the question of how to make the exam most useful. The purpose of an exam like this is not to get grades for you guys, although that's an incidental byproduct. The purpose is to give you some feedback on how you're doing and how your command of the material has evolved, and also to help you sort of learn some of the things that you might not have mastered. So the way the exam is going to be structured is going to be about 50 minutes of short answer questions, a couple of very short computations, but mostly short answer questions on paper. You'll hand those back, and we'll go over those questions in class afterwards. Okay? So it's a relatively low-pressure exam, and it's mostly conceptual. It will cover everything we've done through this last problem set. To the degree that we get to the lecture part of today after questions, today's lecture will not be directly covered. However, it will be fair game for the next midterm, which will be more of a traditional midterm, and that's coming in April. So the structure of today is I'm going to give you a whole bunch of clicker questions, so make sure you've got your clickers out. And those clicker questions are going to give you a sense for the level and scope of the exam. The exam will be a little harder than the clicker questions, but not a whole lot. And the difference is just that it's going to be on paper in front of you instead of clickered, and thus that gives you a little more room to do calculations on a piece of paper. Short calculation. And then after that, we'll come on to some, in some sense, of a review, but also an introduction to the Dirac-Brock head notation that many of our textbooks use, but that we haven't introduced in lecture so far. Okay, any questions before we get started? 41. Other questions? I think there will probably not be a practice exam because of the shift in format. Today will basically be your practice exam. If I can get my work together and get you guys a practice exam of the right format, then maybe, but it wouldn't even be all that useful, is the problem. So watch what happens today. Yeah. I will post the questions from today on the website, yes.
So it's 50 minutes short after there a certain number of questions.
I'm not going to tell you that. But it's not going to be a time trial. Okay, you're not going to be racing to get the...
Will it still be worth it?
It will, because to my mind, part of the reason to design the exam this way is that it's testing your conceptual understanding, which is the important thing. So